Welcome to my presentation for the SWST annual meeting. Innovative high feed rate additive manufacturing using sustainable nanomicro cellulose reinforced thermoplastic composites. What is large-scale additive manufacturing? Well, this little video here will show you what I'm talking about. Basically, it's taking 3D printing to a much larger scale than typically you would enable. But basically, we have a large 3D printer at UMaine, and we printed a boat in 72 hours. It was 5,000 pounds, 25-foot long. It also won 2 Guinness World Records for the world's largest 3D printed boat and the world's largest 3D printed object. And basically, this kind of shows you how the process works and the type of thing that we're planning on doing in the program. The project I'm going to be talking about a little bit is basically a partnership between the University of Maine and Oak Ridge National Labs, where we're focusing on additive manufacturing of bio-based composites. This is really the first time that Oak Ridge has entered into a partnership with a university that's in a different part of the country, in the Northeast, in our case. And basically, this was an outgrowth of an assessment that was done about 4 years ago when a bunch of paper mills in Maine were closing. We're trying to figure out what's a way that we can, look at new types of technologies for the forest products industry. So we partner with Oak Ridge, and they have the expertise in additive manufacturing, whereas Maine has expertise in bio-based composites and structures. And the program that we started is a $20 million 3-year project where we're looking at additive manufacturing for bio-based materials. In the current scope of the project, we're really looking at focusing on nanocellulose production and integrating nanocellulose into the composites and additive manufacturing applications. We're looking at ways to try to lower the energy of cellulose production and looking at ways to dry and minimize fiber agglomeration. Also looking at surface modification in polymer composites. Then for the 3D printing process, we're looking at thermoplastic printing, foam printing, and also thermoset printing. And at the same time, we're looking at modeling of the processes and optimization of printing parameters. And then some of the applications that we're going to be looking at will be indirect applications, which are tooling, which is a primary focus, and then functional direct applications where we might do stay-in-place tooling, like for a cement beam for, say, a highway bridge. Again, we're focusing on forest products type applications of wood flour is a good example, and then some of the cellulose nanofibrils. We're trying to come up with green alternatives and lower cost alternatives to carbon fiber filled plastics that are quite costly, in the neighborhood of almost $3 a kilogram. And we figure that with some of the work that we've done with extrusion processing at UMaine, we may be able to get down to a quarter to 50 cents per kilogram for some of these lignocellulosic fiber filled thermoplastic materials. Here's an example of a tooling mold that we did where we combined wood flour and some spray dried nanocellulose into polylactic acid to make a composite. And again, this was printed at Oak Ridge National Lab, and then we shipped it up to Hodgson Yachts in UMaine, where they use this to make a roof mold for a boat. So kind of an example of an application. So lastly, what I'd like to say is this partnership between the University of Maine and Oak Ridge is tackling an important challenge in creating green, energy efficient materials for large scale additive manufacturing. The addition of lignocellulosic fillers can provide improved material properties for the thermoplastic resins and provide opportunities for recyclable, low-cost feedstocks for large-scale additive. And I'd like to thank you for your attention.